Log on, tune in, find out. Another good idea from Cambridge.
So I guess so what I want to do today is two things. So one thing that I want to do is describe the sort of beginnings of this path that goes from real group representations so the real adjective modifies group to algebra, and so well in the course of that I want to return to say more about this Cartan bijection between real forms of a complex reductive group and automorphisms of order 2. Well, algebraic automorphisms of order 2 of this complex reductive group. So that's the plan. So how shall I say? So I have maybe I'll just write it G for now. This is supposed to be a real Lie group, and I defined a unitary representation to be a map pi that goes from G to unitary operators on some Hilbert space. Well, I guess it can still be V. And there's a continuity requirement, which is that the map from G cross V to V is a continuous map. So this V is a Hilbert space, and so it's a metric space from the Hilbert norm, and that's the topology on the Hilbert space. And pi is called irreducible if V has exactly two closed invariant subspaces. Zero and V, and the exactly two part has of course to do with, you don't call the zero representation irreducible for the same reasons as for finite groups or anything like that. but this closed assumption is important. Let me give an example. So if G is SL2R, so this is 2 by 2 real matrices of determinant 1, then I can take X to be the real projective line. So this is space of all lines in R2 through the origin. And you can think of that as the circle in R2, say the unit circle or something, divided by plus or minus 1. It's a nice manifold, and I can take V to be the space of square integrable half densities on X. So what this means is essentially this is functions, well, f of theta on the circle in the plane with the property that, well, first of all, f of theta is that they're even functions because of this dividing by plus or minus 1. And the square integrable part says the integral from 0 to 2 pi of absolute f of theta squared d theta is finite. So that's, well, that's a little bit imprecise, but can be made precise. And at any rate, this is a nice Hilbert space, and the group. I should have said G acts if you have any line. Of course, the group by its definition acts on the two-dimensional, acts on R2, and so it acts linearly, so it preserves lines. So G acts on X, and so if you take a square integrable something or other on X and change coordinates by G, you get another square integrable something or other. And the statement is that well, this is, it's not very hard to see that this is a unitary representation of G, and in fact it's irreducible. That's not very hard, but it's not quite obvious. One reason that I wanted to write this down is to understand what this business of requiring only two closed invariant subspaces. The point is that V has lots of invariant subspaces. You can have bounded functions f in this picture. You could have smooth functions. You could have real analytic functions. All of these properties are preserved by the nice changes of coordinates coming from G. These are all non-zero subspaces of V, but these are all dense in V, so they don't provide counterexamples to irreducibility. So how do you make some algebraic object out of this space? So, well, let me do it in this case. So this is Harishchandra's idea for how to algebraicize this V. And what Harishchandra said was that you should take this subgroup SO2 inside SL2R. So this is just rotations of the circle. It's a very nice subgroup. And well, that's this squiggle here. They aren't really functions. They're half densities. If it were functions, how do I say it? The measure d theta here is not preserved by the group. And so it isn't a good idea to talk about functions on the circle. With respect to, I mean, what I've written down here is a perfectly good Hilbert space, and the group does act on this by change of variable in the functions, but that action isn't unitary because the action of the circle doesn't preserve this measure. There's a calculus exercise to see what happens if you do this kind of change of coordinates on the circle, but it doesn't preserve this measure. So in the action on square integrable functions, it isn't unitary. What I have to think of is an object in the Hilbert space is really something that looks like this. And the way the group acts is there's some Jacobian factor for how the measure changes under the group action. So if I put a constant function times the square root of d theta, and I act by something in the group, I'll no longer get a constant function because there'll be a Jacobian factor that messes it up. So, yeah, I mean, that's a very good point, but it's because I was being sloppy. Okay, so what do you do with these well, let's see. Let's what you can do inside V, you can take what VK. So these are the K finite, well, L2 half densities on the circle. And what this means, these are half densities whose various rotational translates. So instead of using arbitrary projective linear transformations, you just use rotation. The rotational translates span a finite dimensional space. So that's the definition of this space. And what it is, it's things that look like, well, I guess I could write am e to the im theta, well, something like this, where all these AMs are complex numbers, and AM is equal to 0 if M is odd. So, I mean, I could have written 2M or something like that, but this is the evenness condition that I've got going on everywhere. So any function on the circle has some sort of, well, any reasonable function on the circle has a Fourier expansion, and the condition to generate a finite dimensional space under rotation is that Fourier expansion is finite. So in other words, this is the span of, well, these e to the im thetas. So this means span in the algebraic sense. We're back to the world of algebra now. This is a nice countable basis. And what happens? Let's do it here. So I suppose it's possible that this interference is my cell phone, isn't it? I figured if I was sitting in the back, I could do whatever I wanted, but maybe here I have to be good. So, what Harishchandra proved. So let me make another. Definition. So this is back in the world of a say unitary pi of this Lie group G. So a vector V in V is called smooth. If the map from G to V, which sends G to pi of G applied to V, is differential, it is C infinity. And it certainly implies that, and I have to think about whether it's equivalent. I mean, a normal person learns calculus in one variable. If you go to France and you study from Dieudonné, this is where you define differentiable. You have maps into, well, the difference is I have a Hilbert space. Sorry?
Maps of two-bounded manifolds or something.
Absolutely.
Okay.
There's perfectly good notions of differentiable and so on. This is all fine. And so V infinity is by definition the space of smooth vectors in V, and now I forget. I guess for some reason I'm blanking out on who this is due to. Maybe it's not. Godemont isn't the right name. The statement that this is dense in V. I'm blanking out on the. I'm pretty sure it's not Godemont, but at any rate, the fact is that V infinity. Sorry. Garding. Yes, thank you. Yes, I was alphabetically close. what Garding proved is that V infinity is dense in V, and V infinity carries a representation. I should have said all these Hilbert spaces are complex vector spaces. So V infinity carries a well, it's a dense subspace that even that's not quite obvious. A dense subspace of V, and it carries a natural complex representation of the Lie algebra of the group G. Okay, so with that aside, then I can say that Harshchandra's theorem is that, well, first for this SL2 example where I've written everything down, but I'll say that it's very general. It says that Vk is contained in V infinity, and it's an invariant subspace. For this Lie algebra representation. And so we have representations of the Lie algebra G and the compact group K on this Vk. Well, they're jointly irreducible. There's no proper subspace preserved invariant for both of them. And in fact, if G is connected, as SL2R is, then it's actually irreducible just as a Lie algebra representation.
Do you want a semi-simple though?
Well, for the moment, I've just said SL2, and now I want to say in what generality this is true, yes. So now this is a nice thing. So the generalization that Harshchandra actually proved, so I don't want to be completely precise about what a real reductive group means, but it's certainly okay to have the real points of a complex reductive algebraic group. That's defined over R. And well, a maximal compact subgroup K inside of G, which means exactly what it sounds like, a compact subgroup which is not contained in any larger compact subgroup. This is unique up to conjugation in G. And so if we have V an irreducible unitary representation, you can perfectly well define Vk, the k finite vectors. These are the vectors belonging to a finite dimensional k invariant subspace. And then the theorem is still true that these k finite vectors are smooth, and so you get both a representation of the group K and a representation of the Lie algebra G with this joint irreducibility condition. So that's part of the theorem, and in fact, so how shall I say this? So Arun wanted me to have a category, so I should have a category. Well, I should let me just say in this SL2R example, so the Lie algebra G is 2 by 2 trace 0 real matrices, and its complexification is 2 by 2 trace 0 complex matrices. And well, always there's some triviality complex representations of a real Lie algebra G are essentially the same thing as complex representations of, well, this is GC. You can always complexify the Lie algebra without doing any harm. So in our case, this GC has a basis H, E, and F, except I don't want to use the ones that you think. I want to take H is 0, I, minus I, and 0, or something like that, and heaven only knows what E and F are. Let's see how that looks. That has determinant -1.
But they still have usual relations.
They do have the usual relation. You've got it. That's right. And writing down F is an exercise for the reader. So well, also the question of whether I got this sign correct is an exercise for the reader. So the point is that in this Lie algebra representation, the action of h on this e to the im theta sort of function, well, d theta to the 1/2, whatever, is just, well, who knows whether it's plus or minus m times this function. So if I call this Vm, and then E applied to Vm is some constant times Vm plus 2, and F applied to Vm is some constant times Vm minus 2. So this should make you feel almost at home. These are very familiar kinds of SL2 things. Okay, so, but I promised to write a category. I'll write it over here because it says this board cannot be seen clearly by the audience. So that's a good place to put a category. So the category, remember I have this real reductive G and K maximal compact. What happens is that K acts on this G is the Lie algebra of G by automorphisms. This is the adjoint action. In fact, even G does, but I only care about K at the moment. And so we'll have a category. So it's my inability to make these script letters is the source of my problem with categories. So that's all it is. So M of GK, this is the category of GK modules. And well, so the object, an object is a complex vector space. Let me write it X. I don't want to write V because it's really VK. It's a complex vector space X with two things, a representation of the group K and a representation of the Lie algebra G. And those two things are supposed to be related in a certain way. The first condition is the action of K is locally finite and continuous. So that means that any vector in X generates a finite dimensional space. If you move it around by K, you get a finite dimensional space. And, well, I'll continue the category over here. So, what did I call that? 1? I didn't call it anything. Oh, 1. Okay. So, by this, oops. So, now I've done it. Okay, but by condition 1 plus sort of finite dimensional Lie theory, this representation of K differentiates to a representation of the Lie algebra of K inside of G. And condition 2 is that this differentiated representation is the same as the restriction of this G representation. So in this SL2 case, this H is in the complexified Lie algebra of K, and if you differentiate this function, differentiate the action of K, that's where this M comes from. So that's the second condition. And the third condition says that if, I don't know, Z is in G and K is in K, and X is in X, if I act by in that order, that it's the same as I push the K past the Z like that. So I sort of conjugate K past the Z, and the two actions match up. So that's what a GK module is. I won't tell you what the maps are. Well, I mean, I won't write it. They're linear maps between vector spaces that respect all of these structures. So let me so what I've done with Harichandra's theorem, so he would roll over in his grave, but what he's done is made a functor which goes from unitary representations, anyway, irreducible representations. Well, if you have the word irreducible, it's not much use saying functor, to GK modules. So that's what, that's, these objects are called GK modules. And we'd like to know, well, I said I wanted to have a path from understanding these things to algebra. In order for this to be a path, I need to know about how to go backwards also. So let me say something about that. So I'll say that an invariant Hermitian form on a GK module X is a mapping from X cross X to C, which is sesquilinear. So it means C linear in the first variable, and C conjugate linear in the second variable. Well, and I don't know, x prime is equal to x prime x complex conjugate. These are the words. This is what I mean by Hermitian. And what I mean by invariant is that this should be preserved by the action of the group K. That's easy enough. And, well, in a sense, the differential of preserved by G. So what that means is that Z applied to x prime is minus x Z dot x prime. This is for any Z in the Lie algebra, and x and x prime in X. So that's fine, and this form is called positive if x is bigger than 0 for all x not equal to 0 in X. So those aren't very hard definitions. And what's almost transparent is that Harichandra's theorem carries unitary irreducible representations to, well, I said irreducible and with a positive invariant Hermitian form. So just the form from the Hilbert space comes along for the ride. Since this is supposed to be instructional, I should perhaps give some hint about how Harichandra's theorem is proved. But I'm not going to, I guess. Too bad. So it isn't incredibly difficult. It's extraordinarily clever. I mean, there's just a whole slew of amazing ideas in the proof, many of which are fundamental to algebraic representation theory. I mean, for example, Harichandra's analysis of the center of the enveloping algebra is at the heart of many, many things, and that's part of, I mean, he made that analysis in part in connection with this theorem, but I won't say more about it. So here's here's what Harichandra finally proved. So this is very long ago. That well, this functor makes a bijection. That goes from irreducible unitary representations of G, And there's some obvious functional analysis definition of unitary equivalence. And these irreducible GK modules with a positive invariant Hermitian form. So that's how the problem about unitary representations becomes algebraic. So this is a completely amazing theorem. Just to tell you one other thing to be impressive about Harishchandra. So one of the basic theorems that everyone should know about representation theory is what's called the Borel-Weil theorem, which tells you how to realize representations of either compact groups or algebraic groups in characteristic 0. It's a wonderful theorem. Of course, like many theorems named for people, you can go and look for the papers of Borel and Weil which prove this theorem, and you won't find them. They don't exist. The theorem is proved in a Bourbaki talk by Serre, explaining, I mean, he attributes it, the ideas are due to Borel and Weil, and it's one of the things that everybody knows about Borel and Weil. In fact, Harishchandra published this theorem at exactly the same time as Serre's lecture. He published a much more general theorem about highest weight, infinite dimensional highest weight representations for real groups. But it certainly, in the case of compact groups, was exactly the Borel-Weil theorem, and it's published under his name with a complete proof. And it's not called the Harishchandra Borel-Weil theorem, but it is. So this is a clever man.
That's too clever, right?
Sorry?
That's too clever, in a sense.
I don't know.
Perhaps if you were less clever, this theorem would be attributed to him.
Ah, that's interesting. I don't know. I mean, we could talk about the Bruja decomposition, which I think my recollection is that Bruja proved this for classical groups, and Harishchandra, it's the Harishchandra decomposition. That's at any rate. So I want to. We're in a moderately algebraic world now. So what I want to do is make GK modules more algebraic. So one thing I already did, which is to replace this real Lie algebra G by its complexification. So this is just completely harmless. Nothing changes. There's one little thing that you need to keep in mind, that this GC now has a complex conjugation bar on it, and this invariance condition looks like z dot x prime is minus x z bar dot x prime. This is for z in GC, because if you take this Lie algebra element and multiply it by I, on this side the I comes out, and on this side the I comes out with a minus sign. And so to take care of that, you need to write that, but nothing serious. So now we're talking about representations of a complex reductive Lie algebra, which is nice. So the other thing that you may not like is the group K. So here's the theorem. It says that K is any compact Lie group then C infinity of K has inside it the matrix coefficients of finite dimensional representations. And this, well, this is a subalgebra of C infinity of K, and in fact it's a Hopf algebra, and so what should I call? I don't know. I'm not sure a good name for this, but maybe R of K is not terrible. So you can make an algebraic group spec of that Hopf algebra, and that's what's called KC.
Complex valued functions.
Yeah. I mean, these are complex representations, so complex valued functions. That's right. So, yeah, I mean, everything complex. So this is a complex algebraic group. I mean, this is a finitely generated algebra by easy representation theory, and so this is a reasonable object. Of course, you're allowed to evaluate these functions at points of K, so this contains K in an obvious way. And what happens is that algebraic representations of this group KC are the same thing as these locally finite continuous representations of the compact group K. And I should say that this KC is it's allowed to be disconnected if K is, but it's a complex reductive algebraic group. And you get all of them in this way. In some sense, compact Lie groups are categorically the same thing as complex reductive algebraic groups. So complexifying the Lie algebra was a triviality. Complexifying the group is not much more difficult. And so the second thing I want to do is replace K by this Kc. Okay, and so now what happens? Let's see. So I'll just write it once more. So this is a complex reductive Lie algebra. And this is a complex reductive algebraic group. And well, it's also true that this acts on GC by, maybe I'll call it add C just for fun. And well, so these are complex representations of GC and at the same time algebraic representations of KC, and there's some compatibility between them, which is exactly like what I had before. And what I'm saying is that the category M of GK, it really just is the category M of GC KC, in the sense that the objects are exactly the same. If you have an object here, there's the vector space is the same vector space, and the actions of these Lie algebra just naturally give a representation of this Lie algebra. The action of this compact group naturally gives the action of this group Kc. So these functors are as equal as functors, or these categories are as equal as categories can be. And so this is the world that I want to study using, well, everything is complex, flag varieties. Let me just finish by saying what I was going to spend the second half of this lecture on. I'll just say very quickly, in this Cartan bijection from real forms of this GC, this algebra automorphisms of order 2, call these automorphisms theta, of order 2 of GC. Well, here you have this real reductive group, and this K of R, which is maximal compact. And then you can complexify. I explained how to complexify a compact subgroup, and what you get is the fixed points of theta on GC. So that's the relationship between these two pictures. Well, I'll say that again at the beginning on Thursday, but now I will stop. Yes.
Is it always true?
Yes.
So
there are real semisimple groups that are not real points of yeah. So there's some difficulty there. But if you start with a complex algebraic group and take its group of real points and take the maximal compact subgroup, then and complexify that maximal compact subgroup, you do indeed get the fixed points of this automorphism.
Point was just the connected.
No, it's exactly the fixed points. This group may be disconnected. So if you start with GLNC and GLNR and the real orthogonal group ON, which is disconnected, then I said that this automorphism here was inverse transpose, and the fixed points, well, the fixed points of inverse transpose on GLNC, this is the complex orthogonal group, which is disconnected. Everything matches.
So perhaps we can discuss this later. I mean, there was some theorem that if you take, simply, so it seems that we proceeded to questions. When you take some connected algebraic group, and
then the fixed points of theta are necessarily
then
connected.
it's connected.
Yes, that's correct.
And I don't really remember what happens when the group wasn't simply connected.
Well, then they can be disconnected. It depends. But
somehow this complexification is always connected.
Well, if this were connected, so this maximal compact subgroup and this group have exactly the same component groups.
Yes.
That's part of Mostow's theory of maximal compact. So this is connected if and only if this is.
Okay, but now let's this be connected, then complexification is connected. Right?
Yes.
But if I'm not mistaken, in general, the group above is not connected.
Well,
Okay,
but
yeah,
if you made this disconnected, then this one came out to be disconnected to it. I'm happy to look at a counterexample, but I mean, you're right. Both things can happen, connectedness or disconnectedness, but they happen at the same time. This is exactly correct. This is, I mean. If it was my theorems, you'd have me sweating and worried. But we're talking about, Dan Mostow and Elie Cartan, and so, forget it. You lose. Yes.
What's the difference between the algebra group KC and the complexification of K?
It's the same. That's how do I? That's what I mean by the complexification of K, is this algebraic group constructed in this way.
Are there further questions? And we can thank the speaker twice.